Um, Good morning, my YouTube viewers. It's Crystal here. I'm just here this morning because I wanted to give you another code review. And the code review is going to be can you use RNN, that's a recurrent neural network, to analyze and forecast on Bitcoin. So RNN is a recurrent neural network. It's a type of deep learning, and it's one of two broad types of artificial neural network are characterized by direction of flow of information between layers. It is a bidirectional artificial neural network, meaning that it allows the output from some nodes to affect the subsequent input to the same nodes. Their ability to use internal state memory to process arbitrary sequences of inputs makes them applicable to tasks such as handwriting recognition and speech recognition. And in this case, we're going to try it out on forecasting Bitcoin. So what I did was I created this program in Google Colab, which is a free online Jupyter notebook. First thing we did was we imported the libraries that we were going to need. So we imported pandas, which creates data frames and processes data. We imported NumPy, which creates NumPy arrays and performs numerical computation. We imported datetime to timestamp the dates. We imported math to perform some more mathematical computations. We imported sklearn to provide machine learning functionality. We imported Matplotlib to visualize the data. And then we also imported Seaborn to statistically visualize the data. We used Bitcoin. I can't tell you the website that I use to get the Bitcoin because I'm using a free video maker, but what I'll do whenever I make the blog post is I'll give you a link to the website that I use, but it's a Bitcoin website, and sorry I can't show that on the screen at this time. But what you have to do is you have to download it, and then after you have downloaded it, then you have to save it into your computer and use it, which is what I did. And then so I use pandas to read it, to read the Bitcoin file. And so you had to start, end, open, high, low, close, volume, and market capitalization. And so I decided that we checked the info. You can see two of them are objects and the rest of them are floats. Check for null values. There's not any null values, so that's good. So that means that we don't have to impute anything. If we did impute anything, we probably would have to use pandas to impute it because it would be a time series. Timestamp. We're going to timestamp the end because the end is one of the features that I wanted to use, and we're going to use date time to do that. We're going to define the features being end and close, and closing BTC equals DF features. So now we've got a website, a data frame with just end and close on it, which is what I want. So we use Matplotlib to determine the close, to make a graph of the closing price, and you can see how the prices peaked in 2024. I created a histogram of the closing prices so you can see what the closing prices look like in Seaborn. So I used Matplotlib to do a month-wise trend for 2023. So I decided just to do a trend for 1 year, and this is what you see in 2023. And then we decided we were going to do October to December 2023 so you can see what it looks like there. So now we're going to use a seasonal decompose, which is with stats models. So we have an additive decompose, and then we have a multiplicative decompose, and then we have an additive decompose. And then if you're really into time series analysis and you want to study it, then you can study it. You can get the trend and the season and the residuals out of it. Now what we're going to do is we're going to extract the features. So we're going to get a year, month, day, day of week, and weekday name by extracting the features. And then so we're going to make another data set doing that. So you can see close, year, month, day, day of week, weekday. And so I've made some box plots for the months. And so you can see which months have the most activity. Looks like month number 4, maybe April. And then you can see the years. You can see which years have the most activity. So 2024 looks like it has the most activity. You can see the day of the week, and those are very close, very similar. It doesn't really matter which day of the week it is. And now what we're going to do is we're going to resample the time. And so this is what it looks like, the yearly closing at the end of the year. This is the activity at the end of the year. This is the activity at the beginning of the year. This is the activity for each month. So you can see that in 2024 you have a lot of activity. So now what we're going to do is we're going to roll it. And I had to say Windows as 1 because it wouldn't allow me to say Windows as 0. And we're going to roll it by 30 days. And then when we roll it by 30 days, you can see how the time series is smoothed out when you roll it. Now we're going into the deep learning, which is the reason for this video. So we're going to create a data frame called MLBTC, and it's got the features of end and close, and end is going to be the index. So, and then what we're going to do is we're going to have to reverse the data frame. And the reason why we have to reverse the data frame is because the highest date is at the top and the lowest date is at the bottom. And we don't want it to look like that. So we reverse the data frame. So now you can see the data frame as it has been reversed. Okay. Probably don't need that. Probably don't need that one. Because that's just extra, so that's not necessary. And then now what we're going to do is steps. And so we're going to do steps. And so we have to split the data frame up into training and data, training and testing, or training and validation. So 80% is going to be your train lin. So your train lin is 80%. So your train data is going to be 80% and your val data is going to be 20%. So this is our val data. So you can see the val data. And now we're going to scale it. You were going to use sklearn's min-max scaler to scale it to keep it dimensionally close. So you're going to scale your training set, and you're also going to scale your validation set. So now we have X train, Y train. And then what you do at an X train, Y train is you're going to range it of 50 and then to the length of the scaled train. And then it's going to give you X train and Y train, but it's going to go up 50 points to do that. And then you're going to append all of that. And it says if I is less than or equal 51, you print your X train and your Y train. And then we have to do that with the validation set too. We have X val and Y val. And then so you have to up it. You have to increase it by 50. So the first 50 points or 50 steps is going to be used to make the prediction. So you have to step it by 50. And then we have to we have to take the X train, Y train, X val, Y val, and convert those to NumPy arrays. And then we have to reshape X train, Y train, and X val, Y val. And so we're going to reshape them as well. So you can see what it's like when we have reshaped them. So now we're going to import the TensorFlow libraries so we can use the RNN. And what we're going to do is we're going to do a simple RNN. I went ahead and set the seed just to make it accurate. And then now what we're going to do is we're going to use the simple RNN that I got from some Geeks website. And it has a regressor, a sequential, and then you have a layer of a simple RNN with 50 units, and it has a 10H activation, and it has a dropout of 0.2, and then it has another layer of simple RNN with 50 units and 10H activation. Return sequences equals true. And then you have another layer, which is a simple RNN with the units is 50, activation is 10H, return sequences equals true. And then we have another layer of simple RNN, units equals 50. And then, so we're going to add to the output layer. We're going to have output layer. Output is 1 unit, and activation is going to be sigmoid. So we're going to compile our RNN, and when it says the activation is sigmoid, it's going to give you a value between 0 and 1. And then what happens when you actually use it for binary calculations, then anything less than 0.5 would be 0, and anything higher than 0.5 would be 1. But it's still going to use sigmoid in this instance. And then after we have added our output layer, we're going to compile it. We're going to use SGD, that's stochastic gradient descent optimizer. And we're going to use the loss of mean squared error. And then we're going to fit the model. So we're going to history equals regressor.fit, X train, Y train, 20 epochs, batch size equals 2, and then there's your regressor. So we train it for 20 epochs, and then we print out the summary. And now what we're going to do is we're going to plot a graph of the history. So you can see that the noise goes less. The noise is less as the epochs increase. And so in theory, we could have increased it by made 30 epochs, and there's a possibility that our noise could have increased further. But we just kept it at 20 epochs because it takes a long time to train it. And now we're going to predict on the validation set. And these are your predictions on your validation set. And now what we have to do is we have to reverse scale it. And the reason why we reverse scale it is because, well, you just do really, because if you scaled it at the beginning of the program, then you have to go back and reverse scale it at the end of the program. So there we go. We reverse scaled the Y val, the validation, your Y val. And then we reverse scaled the prediction. So you have to reverse scale the validation Y val, and then you have to reverse scale the prediction. So, and then you get your shape of your prediction, and then we check the RMSE, which is the root mean squared error. So the RMSE still isn't great, but if you watched my previous video on how to do it with machine learning, you'll see that the RMSE is better with the RNN than it was with the random forest. So now what we do is we create a data frame of the actual values and the predicted values, so you can compare the actual values to the predicted values. And then what I do is I use Matplotlib, and I take the prediction line, which is the dashed line, and I overlay the actual values against the prediction line, and you can see it's very close. And after I've done that, I've used Matplotlib to plot the time series. So you can see the red is your training set, the green is your true set, is your validation set, and your yellow is your predictions. And so you can see that the predictions are pretty close to the true values. So that's pretty good. That's telling you that this was a pretty good model to use. It's definitely better than the random forest model, which is why I decided to go ahead and make a video on it. So I'm going to go ahead and close this video for now. If you like my video, please like and subscribe. I would like to thank my subscribers for supporting my channel, and I look forward to communicating with you in the next video.